Hello, welcome everyone to another edition of Symmetry in Newcastle. This time, a very special one because we're having it on Monday instead of on Friday. And our speaker is Henry Bradford from University of Cambridge, and he will be talking about quantitative, locally embeddable into finite groups and topological full groups.
Okay, thank you, Michael, for the invitation to speak today. I don't know what I imagined my first seminar talk in Australia would be like, but it certainly wasn't this, but thank you very much for having me. And thank you all for those of you who are in Australia for turning up in your evenings to hear me speak. I'm not a morning person by nature, so thank you for being so accommodating. So in terms of the practicalities, I have got a second tablet trained on an actual physical, honest-to-goodness piece of paper here on which I'll be writing, which I think is spotlighted, so you can all see that as your main image. Okay, so yes, I'm going to be talking about quantitative LEF and topological full groups, and everything I'm talking about today is joint work with Daniele Dona, who's a postdoc in Jerusalem and was formerly my colleague at the University of Göttingen. So to start with, I'm going to make a very innocuous statement. Which is that the integers modulo k form an approximation to the integers. Okay, so this is, hopefully shouldn't strike anyone as controversial. It's a principle that's used throughout mathematics that if you want a finite model of the integers, you work modulo k. This might mean different things to different people in different branches of mathematics, but I think to a group theorist, what it's generally taken to mean is the following. So we have a homomorphism pi k, which is reduction modulo k, a surjective homomorphism from the integers to the integers modulo k. This is a homomorphism. And for all finite subsets f of the integers, there exists a k such that the restriction of pi k to f is injective. In fact, of course, the conclusion will be true for all sufficiently large k. So another way of saying this is that the group Z is residually finite. So if you've not seen the definition of a residually finite group before, it's just the same as saying that for every finite subset of your group, there is some finite group and a homomorphism to that finite group from your group, which can be made to be injective on any finite subset of the group. Okay, fine. Now let me give another seemingly similarly innocuous statement. Which is that the following group, the wreath product of S3 with the integers modulo k, which is to say S3 to the k semi-direct product with the integers modulo k, where the integers modulo k acts on the product of k copies of S3 by cyclically permuting factors. That this is an approximation to S3 wreath the integers. So here I mean the restricted wreath product, so the semi-direct product of the direct sum of Z many copies of S3 with Z. So I claim that this is similarly innocuous because, well, if Z modulo k is an approximation to Z, then surely any group I any group I build by plugging in Z modulo K is an approximation to the same construction plugging in Z instead. However, there's a problem here with saying that these are similarly innocuous statements, and that problem is that S3 read to Z is not residually finite. Okay, and I'm just going to quickly give the proof of this because it's very benign. So if I have G and H permutations in S3, which don't commute with each other, I can define corresponding elements of the base group, the direct sum of Z many copies of S3 as follows. So I'll define Gj to be the tuple of elements of S3 in the base group, whose ith element is G to the power Kronecker delta Ij. So in other words, this is G in the jth coordinate and trivial everywhere else. Okay, and likewise for H. Then, okay, I'm going to try and apply the definition of residual finiteness and see what breaks. So if Q is a finite group and pi from S3 read to Z to Q is a homomorphism, then, well, Q is a finite group. Its restriction to Z can't be injective, so it has to have non-trivial kernel. So there's some non-zero integer in the kernel of pi. And now I consider pi applied to the commutator of G0 H0. So this is a non-trivial element of the wreath product because G and H don't commute. And I claim that it's in the kernel of pi. Okay, so that would mean that there is no homomorphism to a finite group in which is injective on the set consisting of the identity in this commutator. So residual finiteness would be broken. And why is this the case? Well, because I have a non-trivial integer in the kernel, after mapping by pi, nothing changes if instead of the commutator of G0 and H0, I have the commutator of G0 and the conjugate of H0 by Z, which is just the same as pi of the commutator of G0 and Hz. So now I have a commutator of two things in a direct sum of groups. One only has non-trivial entry in position 0. The other only has non-trivial entry in position Z, which is non-zero position. So in every position, I'm taking the commutator of something with the identity. So I get the identity at every coordinate, therefore the identity overall. Okay, so this group is, it's really easy to show that this group is not residually finite. This was a very elementary argument. And of course, this would work not just for S3 at the bottom, but any non-abelian group. But I would still quite like to say that S3 wreath Z modulo K is an approximation to S3 wreath Z. That seems like it should be true morally. So to do that, I'm going to need a different definition of approximation. So that brings me to the first definition from my title, which is LEF. So what does it mean for a group to be LEF? So the group gamma is LEF, or locally embeddable into finite groups, or LEF for short, if the following thing holds. So again, we're interested in all finite subsets of our group gamma. And we want to see those finite subsets modeled in finite groups. So for residual finiteness, this meant we took a homomorphism from gamma, which was injective on F to a finite group. The Reith product example shows that we can't do that. And the reason we couldn't do that is when we took a finite quotient, we had this sort of looping around phenomenon where coordinates which are distinct and therefore commute in the infinite group become identified and therefore don't commute in the finite group. And that gives us a contradiction. So LEF just says, okay, let's just ignore this wrapping around phenomenon that homomorphisms force on us and just cut our finite subset out of our group gamma and map it into a finite group. And we don't even need to define what our map does on the rest of the group. So that is to say that there exists a finite group Q and a function, an injective function from the subset to our finite group Q. Okay, well, we need to preserve some group structure for this not to be a completely trivial definition. So I'm just going to, so we just say that the homomorphism property is satisfied wherever it is well defined. So in other words, for all pairs of elements in our finite subset F, if the product is an R set F, if it's in the domain of our function, then the homomorphism relation is satisfied. Okay, and such a map pi, if it exists, is called a local embedding. Okay, so this property was introduced by Grigorchuk and Medynets in the 90s, and it's been studied by lots of people since then, from various points of view. So let me give a few examples of groups that have this property. So first of all, I mean, this is clearly a weaker property than residual finiteness. If you just apply the definition of residually finite and forget everything that's happening of your homomorphism outside the set F, that verifies that your group is LEF. So indeed, any locally residually finite group is LEF. For example, any group with a faithful representation of the fields, a linear group, or any nilpotent group. Okay, many other examples. So I said that this was a modified notion of approximation to deal with the fact that Reith products could very easily not be residually finite. So that suggests that Reith product should be LEF under reasonable conditions. And indeed, that was one of the first examples that Grigorchuk and Medynets dealt with in their paper introducing LEF. So if delta and gamma are LEF groups, then the restricted Reith product of delta and gamma is LEF as well. And as we saw with my little toy example, F3 root Z, this is very much not true if we replace LEF with residually finite. So if you like, this is an advantage of LEF as an approximation property over residual finiteness because it is preserved under some natural group theoretic constructions that residual finiteness isn't. The final example, which is going to be my main focus today, and this was a theorem by Grigorchuk and Medynets, 2012. So they proved that topological full groups, Cantor minimal systems, are LEF. Okay, so that's going to be my main focus in this talk, talking about this theorem and some refinements of it. So in particular, my interest in this property LEF is I'm interested in how you quantify it. In other words, for a given finite subset F of my group gamma, how big does the finite group Q have to be to afford a local embedding of the finite set F? Well, that might depend very much on the finite set F that we take. We want some kind of concise description, maybe some archetypical finite set F, on which to test the size of these finite groups affording local embeddings. Well, if I'm working in the context of a finitely generated group gamma, then there are some very natural finite sets, which are the balls in the word metric. So that will be my definition of quantitative LEF. So if gamma is LEF and finitely generated by a subset S, I define the LEF growth of gamma with respect to S to be the following thing. So I denote it as curly L subscript gamma superscript S, and it's a function which takes integer arguments and returns an integer value, and it is just the minimal order of a finite group Q such that there exists a local embedding from BSN Q, where BSN is the ball of radius n in the word metric induced on gamma by the finite set F. Okay, so why are the balls archetypal finite sets? Well, any finite set will eventually be contained in one of these balls, and the balls are nested, they're indexed by integers, so this gives me a very concise way of expressing every finite set in terms of something that I can just plug an integer into and get an integer answer out of. So just a couple of quick remarks about this definition. Like every invariant of finitely generated groups, that geometric or asymptotic group theory study, the definition depends on the generating set, but it doesn't really. So the dependence on the set S is very slight. And I'm going to just assume throughout that we're studying the LEF growth up to some natural notion of comparison of functions. I'm not going to belabor this point, but let's just say we can rescale both the argument and the output of the function up to a multiplicative constant, and we'll consider such functions to be equivalent. Okay, just as we do in geometric group theory typically. Second observation, we get immediately a lower bound for the LEF growth of any group in terms of another well-studied invariant of the group, which is the growth function, or the word growth function. Right, the word growth function of a group just measures the cardinality of BSN, the ball of radius n. And if I have a finite group that affords an injection from the ball of radius n, then the order of that finite group has to be at least the number of elements in the ball of radius n. So if I have a group of exponential growth, for example, I know immediately that the LEF growth is also at least exponential. Beyond that rather trivial lower bound, lower bounds on the LEF growth are actually quite difficult to construct. If you want to prove an upper bound for your favorite LEF group, all you really do is take the proof that the group is LEF and keep track of everything, of how big everything is in the proof. Now, sometimes there are multiple proofs of the same group that group is LEF, and you maybe have to decide which is the best proof in terms of the effectiveness of the proof. But if you can prove that an upper bound of the LEF growth, that is just a proof that the group is LEF with some effective control. Whereas lower bounds are both difficult and interesting because there isn't really a very strong structure theory for local embeddings. It's very different from the case of residual finiteness, where many groups satisfy strong rigidity properties that restrict, in a strong sense, the homomorphisms they admit, and from which you can deduce a lower bound on the size of finite quotients of the group. But local embeddings are much more flexible, so excluding small finite groups from affording them is a challenging problem. So let me just give you an example of that phenomenon. So I think the notion of left growth was first introduced by Gulnara Argentova and Pierre Chery in work that was discussed for a long time, since they proved these results in about 2008, but actually didn't appear on the archive until a month or so ago. So so they introduced this notion and investigated it for various groups. In particular, they looked at how left growth behaves under taking Reith products. So if I have delta and gamma finitely generated left groups, then the left growth of delta Reith gamma. So first of all, this Reith product is itself a finitely generated group. That was already known from a long time ago. And this is dominated by the exponential of the left growth of gamma, that's the group on the top, times by log of the left growth of delta, that's the group on the bottom. Okay, so this looks like a slightly complicated formula, but all it's really doing is what I said we did for proving upper bounds on the left growth, which is you take a proof of left for Reith product and you quantify it. So what is the proof? Well, if you have a finite subset of delta and another finite subset of gamma, there is a corresponding finite subset of the Reith product that you can build, and a local embeddings from the subsets of delta and gamma induce a local embedding of the corresponding subset in the Reith product. You just do that with balls and see and estimate the size of the Reith product of two finite groups in terms of the finite groups you plug into the construction, and this is the bound that pops out. Okay, so it's very natural. On the other hand, lower bounds for this, we still don't know a great deal. So there are examples where there are local embeddings of Reith products of groups that do not come from pairs of local embeddings of the constituent groups. There are some really interesting examples of that form. So local embeddings of Z Reith Z into finite symmetric or alternating groups, for example, with generating image. So really interesting things. So they can be quite wild. One case where we can say something, and this is something I proved last year, hopefully it'll be on the archive soon, is that as in the case of S3 Reith Z, if I have a finite group on the bottom of my delta, which has trivial center, then the left growth of the Reith product is bounded below in terms of the exponential of the word growth of the group. So already in certain examples, this gives us a much stronger lower bound than the trivial lower bound coming from word growth. So for example, and in fact, it allows us, combining with the Argentova-Chery upper bound, to describe the left growth precisely for many groups. So for instance, if I have the group on the top gamma to be a free abelian group, then the left growth of that with a finite centerless group is just exponential in n to the d. Or for something a little bigger, if I take gamma to be a free group of rank D or SLDZ, for D at least 2, then the left growth of the Reith product is doubly exponential in N. So this is just combining the previous observations of Asymptotic and myself with the fact that we know the left growth of 3 abelian groups, 3 groups, and SLDZ on the nose already, just coming from taking our local embeddings to be familiar congruence quotients of those groups for the upper bound and using the trivial bound coming from word growth for the lower bound. Okay, so this is sort of where we are with left growth at the moment. Now, whenever you have an asymptotic invariant of groups like word growth, like left growth, residual finiteness growth, subgroup growth, lots of other things, there are 3 things that it always makes sense to do. One of those things is to estimate your growth function in some natural examples. So take your favorite group satisfying the property and quantify the growth function for that group. The second thing you want to do is to see what kinds of functions can arise as your asymptotic invariant for some group. So for instance, there are lots of interesting open problems at the moment about what kinds of functions can be the growth function of some group. And for any reasonable invariant, it's natural to ask a similar question. And the third thing is, what does knowing this invariant for a group tell us about the structure of the group or the structure of spaces on which it naturally acts? Okay, so for example, we know that if a group, thanks to Gromov, we know that if a group has polynomial growth, polynomial word growth, then it's virtually nilpotent. So what structural restrictions do restrictions on the asymptotic invariants place on the group? Okay, so I want to talk about all 3 of these themes, and I want to do so with respect to the specific example of topological foregroups. So now I'm going to pivot away from left for a little while and spend a little while talking about topological foregroups. Before I do that, are there any questions so far about what I've said about left groups?
So far, so good, it seems.
Great, let's crack on then. So a change away from group theory now into topological dynamics. So in what follows, X is just going to be a Cantor space, so just some space homeomorphic to the standard Cantor space, and T is going to be a self-homeomorphism of X. So from this data, I'll call the pair of X and T a topological dynamical system. And in topological dynamics, a system is called minimal, if every T orbit under X is dense in X. So it's the natural notion of irreducibility in the setting of topological dynamics for a system. So I'm going to be assuming that our systems are minimal unless otherwise specified. Then, if we have a minimal system, the topological full group of the pair xt is defined to be, so I'll denote it as T with double square brackets around it. It's a subgroup of the homeomorphism group of the Cantor space. And it's a subgroup consisting of those homeomorphisms that everywhere locally act like some power of T. So one way of saying this is that there exists a continuous function, f sub g, from the Cantor space to the integers viewed as a discrete set, such that for every point in X, applying G to that point is just the same as applying T to the power of F sub G at that point, to that point. So this formula is a little bit intimidating if you're seeing it for the first time, but all it's saying is that there is a finite partition of the Cantor space into Clopen sets, such that on every set in the partition, our group element G acts by some power of T, which is constant on that part. Okay. This is just another way of saying the same thing. So the function f sub G is going to be called the orbit cocycle of the element G. It really is well defined because my system is minimal, there are no periodic points. So if I change the power of T by which I act on a point X, then irrespective of where that point is, it moves the point somewhere else. So knowing where I've sent a point X uniquely determines the power of T I had to apply to it to get that. Okay, so why would I define such an object? Well, it turns out to be a very powerful group in many respects. First, within the setting of topological dynamics, knowing the topological full group more or less uniquely determines the topological dynamical system. In fact, you can get away with even less information than the topological full group itself. So this was observed by basically and Medynets, who proved that if you know even the derived subgroup of the topological full group as a group, so just up to isomorphism, this determines the topological dynamical system up to flip conjugacy. Okay. In other words, so the strongest form of determining the system would be two systems that are equivalent if there is a homeomorphism from one Cantor space to the other with respect to which the corresponding homeomorphisms defining the two systems intertwine. Okay, so they're the same homeomorphism, just up to relabeling of the elements of Cantor space. Flip conjugacy is that, except you allow one system to be either equivalent to the other or equivalent to the inverse system, where we just replace T with T inverse. So up to inverting the defining homeomorphism, the derived subgroup of the topological full group uniquely determines the system. Okay, so it's an extraordinarily powerful invariant in terms of topological dynamics. The derived subgroup of the topological full group is also a remarkable object in the context of group theory. So a few kind of sample theorems about its structure. So a lot of the basic group theoretic properties were worked out by Matsui, who observed that the derived subgroup of the topological full group is an infinite simple group, and that it is sometimes finitely generated. In fact, it's finitely generated if and only if X is a minimal subshift. Okay, what does that mean? Well, so this is a particular kind of topological dynamical system. So we have a finite discrete set, we call the alphabet. Then we can model the Cantor space as bi-infinite words, so integer sequences of elements of A. And when we do that, we have a natural homeomorphism of this space called the shift map. It's the homeomorphism that just moves everything one place to the right. And then a subshift is just a closed sigma invariant subspace of the Cantor space in this model and the corresponding system. Okay, so this is a natural source of examples of topological dynamical systems, and these are precisely the ones when the system is minimal that give us a finitely generated group. Finally, a really remarkable theorem, Yushchenko and Monod proved that if the topological dynamical system is a minimal subshift, then the derived subgroup of the topological full group is a finitely generated amenable group. And in fact, this theorem gave us the first examples of finitely generated groups which were infinite, simple, and amenable. So they really are exotic objects from the point of view of geometric group theory. So once again, the theorem I'm interested in today of Grigorchuk and Medynets is that the topological full group of a Cantor minimal system is LEF. And so we know qualitatively that it's LEF, and so we want to understand the quantitative aspects of LEF of these groups. And the slogan is going to be that asymptotic features of the minimal subshift that defines the topological dynamical system will be reflected in the LEF growth function of the derived subgroup of the topological full group. Okay, so the derived subgroup of the topological full group is a finitely generated LEF group. We can estimate its LEF growth. If we know the derived subgroup of the topological full group on the nose, we know it up to isomorphism, then we basically know everything about the topological dynamical system. If we know less about the derived subgroup of the topological full group, if we just know some of its asymptotic features, for example, its LEF growth function, it's reasonable to expect that we may not know everything about the topological dynamical system that gave rise to it, but we should know some asymptotic features of the topological dynamical system. And our results are precisely in this spirit. Okay, so which asymptotic features am I interested in? Well, there are two in particular that I want to talk about. So if I have an element of the shift space, integer sequences on the finite alphabet, and some element of a to the n, some n tuple of elements of the alphabet, then I say that the n tuple b is an n word of a if there exists an integer m such that the m tuple in a the n tuple in a starting at the mth term is just b. So we see the word b inside of a. And then we have an asymptotic invariant, which is the complexity function of the infinite word a, which is just the number of n words of a. Now, this is always at most the number of n words in a to the z. In other words, it grows at most exponentially in n. And we can give a lower bound if the minimal subshift generated by a is minimal. So this is an old result of Morse and Headland. That the word A is periodic, which means the closure of its orbit in the dynamical system is finite, if and only if there exists some n such that the complexity function takes the value at most n at that point. Okay, so I hinted that this complexity function, the periodicity, was relevant to minimality for dynamical systems. So this is, I think, it's a very old, I'm going to call it a folklore proposition. I don't know, it might be due to some specific person, but it goes a long way back. If I take X to be the closed orbit of a word, an infinite word A in the shift space, then X is an infinite shift minimal space if and only if the word A is first non-periodic, give me something infinite, and uniformly recurrent. That is to say, every finite word that appears in A, I can see on any sufficiently long string, any sufficiently long subword, where sufficiently long just depends on the length of the word I want to see. So for all natural numbers n, there exists an m such that every n word of A appears in every m word of A. And right from this definition, you can extract a function that is m depending on n, and that function is my other asymptotic invariant. I just call it the recurrence function. So this is the, so we call it R sub A of n, and it's just the minimal natural number n, such that every n word of A appears in every m word of A. Okay, so I have two asymptotic invariants of topological dynamical systems, the complexity function and the recurrence function. And these are going to be the asymptotic invariants that control the LEF growth of the derived subgroup of the topological full group. So finally, at 10 to the hour, I come to our result, having set everything up. So if I have X and sigma a minimal subshift, and A is some word in X, then first, for the derived subgroup of the topological full group in particular, but indeed for any finitely generated subgroup of the topological full group, the LEF growth of gamma is dominated by the recurrence function of n factorial. Okay, so that's an upper bound. I'll say a word in a moment about where it comes from. Second, for a lower bound, specifically for the derived subgroup of the topological full group, we have a lower bound which is exponential in the complexity function of A of the square root of n. Okay, so upper bounds and lower bounds. For example, if I have a shift which is very deterministic, as close to periodic as you can get, so something like the famous Fibonacci shift, this is a really well-behaved shift space. In particular, both the complexity function and the recurrence function grow linearly, which is about as small as you can get. And so for this example, we almost know the left growth of the derived subgroup of the topological full group on the nose. It's between exponential and factorial in n, factorial being approximately exponential in n log n. So up to this factor of log, we know the left growth exactly, and it's about as small as the left growth function can be because the derived subgroup of the topological full group is a group of exponential growth. So we knew just from the trivial lower bound in terms of growth that it's at least exponential, and that bound is almost best possible up to this factor of log. Okay, so that's a very well-behaved, almost deterministic shift. At the other end of the scale, we can have very wild shifts. So, for example, if you have a subshift of positive entropy, which is just a fancy way of saying that the complexity function grows exponentially quickly, then we apply a lower bound and we get that the left growth is at least doubly exponential in the square root of n. Okay, so the slogan is, if you have a well-behaved, almost deterministic shift, then you have a nice small left growth function. If you have a wild chaotic shift, then you have a large left growth function. Okay, so a question that I feel like I would know the answer to if I knew more about topological dynamics and symbolic dynamics than I do, which is very little, is do there exist any minimal subshifts X containing a point A, I suppose, such that the complexity function of A and the uniform recurrence function of A grow comparably quickly and are of intermediate growth. That is, let's say, strictly faster than polynomial and strictly slower than exponential. There are well-known examples in the symbolic dynamics literature of minimal subshifts with intermediate complexity function, which are uniformly recurrent. It's just that as far as I can tell from the proofs of those results, the uniform recurrence function of those is very, very fast. Finite, but much faster than exponential. So the motivation for my asking this question is really group theoretic. If we had a source of such subshifts, then from our upper and lower bounds on the left growth, in terms of the asymptotic invariance of the subshift, we could exhibit examples of groups with new kinds of behavior in terms of the growth of their, in terms of their left growth. So we've seen some examples of the kinds of functions that can occur as left growth functions. They can be exponential and polynomial. They can be doubly exponential, a few other things. But there are lots of functions we don't know whether they occur as left growth functions of groups or not. And understanding more about the possible complexity of topological dynamical systems would be one way of identifying such examples. Mikhail, how much time do I have left?
You have about 5 minutes, I think.
Okay, great. Then let me just finish by giving a few ideas from the proof of our upper and lower bounds. So as I said, for the upper bound, you just look for the best proof of LEF that you can find and try and keep track of how quickly everything grows in that proof. It turned out, so after a long time looking at Grigorchuk and Medynets proofs, we happened across a second proof by Gabor Elik, which was both shorter and turned out to be more effective in terms of the bounds and the LEF growth that it gave us. So the idea of Elik's proof, which is really beautiful, is that we have a finitely generated subgroup of the topological fold group with generating Z S and some point in the shift space. And for some natural number M to be determined, we consider an interval, which is an interval in the orbit of X under the shift map. So X, sigma of X, up to sigma to the n-1 of X, so an interval of length M. And the aim is to construct a local embedding from the ball of radius n into the symmetric group of degree M. And how will this local embedding operate? Well, it just acts on the interval IM modulo M, right? In the topological fold group itself, an element acts everywhere as some power of sigma. In particular, it will preserve the orbit of any point X under sigma. And we'd like to say we can just cut out this interval from the orbit and say, well, we act on that interval, except that if we go off either end of the interval, then we just loop back modulo M and define that to be where G sends things in this finite image. There's no guarantee that that will work in general, that this will lead to a well-defined map. But if we choose M carefully, such that after we go off the end of the interval, we reach sigma M of X, and if we choose M carefully such that sigma M of X is in a sufficiently small neighborhood of our point X, this thing that I'm claiming is a local embedding is actually well defined. And if also M is chosen to be sufficiently large, let's say dominating the recurrence function, then this map pi is further injected. Okay, and there's just a little argument that says that first that these conditions are enough and that they can be simultaneously satisfied, and we get a local embedding into the symmetric group of something that is so M can be taken to be comparable to the recurrence function, and that gives us our recurrence function factorial. So our target finite group is the symmetric group. So there's some details to check that this can all be made to work, but essentially the idea is Alex. Then for the lower bound, we actually revive an idea that was used to give lower bounds for wreath products. So in some senses, the structure of topological fold groups and wreath products is quite similar locally. And that is we just build a very large direct product of finite centerless groups inside the derived subgroup of topological fold group, all of whose elements of the factors can be expressed as short words in our generating set. And then there's a little group theoretic argument that says that when you have a big direct product of finite centerless groups in your infinite group, a local embedding will see that direct product if it sees all of the factors. Okay, so that's one form of rigidity for local embeddings that we do have, and we exploit that here. And the way that we produce our direct product is again topological dynamical. we want a large supply of small clopen subsets of our shift space, such that we have finite groups acting disjointly, supported on each of those small finite clopen subsets. And we find out that the complexity function, which appears in our lower bound, determines how large a supply of disjoint clopen subsets we have that we can use in our construction. So yeah, by reaching into this world of topological full groups, we were able to find some group theoretically interesting examples of LEF groups for which we could get good estimates, upper and lower bounds on their LEF growth. And we could use those bounds to infer information about the topological dynamical systems from which those groups came. And although this is ongoing work and something for the future, my hope is that this construction will also yield new exotic examples of growth behavior for the LEF growth function. All right, that's all I wanted to say. Thank you very much for your attention.
Thank you, Henry, for your talk. Are there any questions for Henry? Well, does not seem like there are any. So
I guess I have a small question.
oh yeah, go on.
So I guess it's sort of an open question if all hyperbolic groups are residually finite. Is anything known about LEF for hyperbolic groups?
Yes. Thank you, Antoine. So this is something I didn't say about LEF, but which is very important about LEF. Every finitely presented LEF group is residually finite. So in the case of hyperbolic groups, every hyperbolic group is LEF if and only if every hyperbolic group is residually finite. In fact, in general, proving that a group is LEF but not residually finite can be quite a powerful way of proving that a group is not finitely presentable. This gives you not the first proof, but a new proof that derived subgroups of topological full groups are not finitely presentable, for example, because they are infinite simple LEF groups. And there are other natural examples where one can use a similar style of argument. But yeah, for hyperbolic groups, because we already know they're finitely presentable, LEF is equivalent to residually finite.
Thanks.
Okay, any further questions? Well, if not, then let's use our reaction emojis one more time. And thank Henry for his nice talk. Thanks.